In this video, we'll discuss power and give an example or two. So our definition of average power is the rate at which work is done. So delta W delta over delta T. Now if the work rate varies, it could be constant. If the work rate is constant, it's just how much work is done in a given amount of time. In any case, that's going to be your average work. But you might want to know the instantaneous work, and then dW dt is the extension of that. And that is the limit, as delta T approaches zero, of the change in work time. So that shouldn't look too new in concept there. And that unit will be joules per second, the rate at which work is being done, joules per second. How much power is needed to keep an object moving at a constant speed when it's encountering a resistive force, a frictional medium? Well, the power is rate at which work is done, so dW dt. Well, work in basic form is F dot S, or distance over which that force acts, the dot product thereof in particular. But S over T is just really displacement over time, which we know what that is. That's velocity. So power is equal to F dot V, the dot product of the force and the velocity. So there it is. Now this might be a good time, since we've referred to velocity multiple times. The speed in general with kinetic energy is, kinetic energy is 1/2 mv squared. Power is force times velocity. Now, what if velocity goes really high? So we'll just consider the relativistic limitations and how that imposes restrictions at very high speeds. So at normal speeds, kinetic energy 1/2 mv squared. If we plot 1/2 mv squared, we basically get a plot that looks like that. Now along here I've put a particular value, c, and c is the speed of light. And so when we consider the things that happen as we approach the speed of light like mass increasing, if you just think of the mass increasing, then of course the energy is going to increase. Well, it actually does. And the kinetic energy, when we get to very high speeds, changes from 1/2 mv squared to mc squared, speed of light squared, divided by this, you could call it a dilation factor, this 1 minus v squared over c squared. In relativity, this factor shows up frequently, minus mc squared. So that's the value for kinetic energy, and that will give a plot that approaches infinity as we approach c. So it asymptotically approaches infinity for kinetic energy as we approach the speed of light. Well, if we consider the total energy of an object, the total energy is more than that. The total energy is going to be the kinetic energy given by this relationship, this equation, plus mc squared. Mc squared is considered the rest mass energy. So how much energy it has when it's just sitting there, the stuff, the material of which an object consists. So you can imagine, of course, then that if we add the kinetic energy and mc squared, these cancel, and you simply get this mc squared over square root of 1 minus v squared over c squared. It's the total energy contained in a moving object with relativistic considerations imposed upon it. Now, relativity notwithstanding, we will not consider its effects on our problem solving for the most part. So let's do something a little more mundane, which is trying to figure out how many Earth-like spheres can be loaded on a truck in 1 minute. There's the truck. And there you are, loading these 40-kilogram Earth-like spheres with a horsepower average of half a horsepower. How many spheres could you load in a minute? So you're going to lift these up, and here's some more of these Earth-like spheres going on the truck. I'm sure you're wondering what the meaning of all that is, and I'll just leave you guessing. So our average power is 1/2 horsepower. Now, average power can be converted from horsepower to watts. 746 watts per horsepower. So that gives us 373 watts. That's the rate at which work is done. So just looking at the dimensionality of this, the work then is power times time. That's how much work can be done in a given amount of time. So 373 watts times 60 seconds, 22.4 kilojoules. So the number of spheres that can be lifted will be the total work divided by the work per sphere. There it is. And that will give you the number of spheres that can be lifted. 22.4 kilojoules over the work per sphere is force, mg, times the delta y, which is 0.8. And it gives us 71 spheres loaded in a minute. Isn't that an awesome accomplishment of Earth-like sphere loading? In this example, we're going to have a truck engine supplying a constant power P to accelerate the truck. We're going to ignore rolling friction, air resistance, starting at some velocity, well, zero velocity, and demonstrating that these following conditions hold true. Here's the speed at any time. The acceleration is a function of time, and the displacement is a function of time. Now, just looking at those, it looks like that might be a tall order to demonstrate that, but it really won't be. Consider that work done is delta K, the work energy theorem. And, so here's our truck. V00, power is force times velocity. And the work done is just power times time. So work done is 1/2 mv squared, the delta K. Delta K is 1/2 mv squared. And that's the work done, which is power times time. So solve for V. And directly, there it is, square root of 2 pt over m. Now how to get the acceleration? Well, acceleration is dv dt. So 2p over m is the constant part of this, and then the derivative of the square root of t, which is, bring the 1/2 down, t to the negative 1/2, rearranging that, 1 over 2 square root of t, so bring the t inside the first radical, and we have the acceleration, square root of power over 2 times mass times time. And then displacement, the integral of velocity, so there is the constant part, the integral of t to the 1/2, so constant times the 1/2 becomes 3/2, that's brought down, and there we go, 8 square root of 8p over 9m, t to the 3/2 power. That was exciting. Let's do another problem. This time we have a wrecking ball, 3,600 newtons, and the wrecking ball must be lifted at a constant speed for 4 seconds, and it has to go 25 meters. So 25 meters vertically raised in 4 seconds. What horsepower must the engine provide? So we have 3,600 newtons pulling down here. We have to overcome. Move it up 25 meters in 4 seconds. So average power is work over time, which is force, F dot V, force times velocity. The force is going to be upward in the same direction as the motion. So the dot product is just simple here in this case. 3,600, speed 25 over 4. And that gives us 22,500 watts or 30 horsepower.